Welcome to this tutorial of the NLMLapp, which is available as a browser-based app, but also as an R package. The app allows you to build person-specific and pool prediction models with ElasticNet Regularized Regression. Specifically, the app allows you to use the wrappers from this publication with an easy-to-use and accessible user interface. In this publication, the wrappers were used to build person-specific and pool prediction models for binge eating, alcohol use, and binge drinking based on daily life data from patients with bulimia nervosa and/or an alcohol use disorder. However, the app allows you to build person-specific and pool prediction models on all kinds of data. The tutorial starts with an introduction into the theoretical concepts that are used behind the scenes in the app. However, if you are already familiar with machine learning, person-specific and pool prediction models, ElasticNet regularized regression, and nested cross-validation, then you can go and skip ahead. The NLMLapp uses machine learning, which stands for a set of statistical methods and algorithms that can learn independently from data. You can use machine learning to do a lot of things. For example, create this image. But in the NLMLapp, we are interested in two applications of machine learning. The first one being prediction, where we want to predict a certain outcome. This means that we're using supervised machine learning. For example, the NLML wrappers were used to build person-specific and pool prediction models to predict subsequent binge eating, binge drinking, and alcohol use in patients with bulimia nervosa and/or alcohol use disorder. The second application we're interested in is understanding. Because we're using ElasticNet regularized regression, we're getting estimates, which gives us an indication of the direction and the strength of the relation between a predictor and a certain outcome. But how is a typical supervised machine learning analysis conducted? Well, let's look at an example. Let's say we've got a data set with a certain outcome and a certain set of predictors. We can't just go ahead and use the entire dataset to train and test our machine learning model. No, we need to split it into a training set, which we use to train our machine learning model, and a test set, which we use to evaluate the performance of our machine learning model. Why is that? Well, machine learning models run the risk of being overfit, meaning that they're way too specific for a certain dataset and how the relation between the predictors and the outcomes are in that dataset, meaning that the performance might not generalize well to new and unseen data. However, that's what we want to do with our machine learning applications. So that's why we need a test set to see how well our machine learning model performs with new and unseen data. So after we've split our data, we can go ahead and take our machine learning algorithm and put the outcome and the predictors of our training set in it. Afterwards, we'll have a trained machine learning algorithm that learned how the predictors are related to the outcome. So then we can go ahead and go to our test data and put the predictors of our test data in. Then we'll get a predicted outcome, which we can compare to the actual outcome of the test set. And we can see how well our machine learning algorithm performs. And in some cases, as with ElasticNet regularized regression, we can also get an idea of which predictors were the best predictors. Now, I've been talking a lot about person-specific and pool prediction models. Well, what do I mean with that? Well, it all depends on which data you use to train and test your model. For example, in a person-specific model, you will use the data of just one individual to train and then test your prediction model, which results in an individualized machine learning model. This type of model can be interesting in a psychotherapeutic context, where one patient comes into your office, after which you follow them in their daily lives with a smartphone application, and then you train your model and see how well it works with that one individual. In a pool prediction model, you use the data of all individuals to train your machine learning model and then see how well it works on one individual. This type of model can be interesting when the data of one individual isn't enough to build a good, valid, well-working machine learning model. Okay, now let's look at the elastic net regularized regression, which is used in the NLMLapp. Elastic net regularized regression is simply a regression with extra steps. Namely, it uses two regularization methods to ensure that the models generalize better to new and unseen data. The first one is rich regularization. What does it do? Well, let's say we've got a regression model with an outcome y, an intercept beta 0, three predictors x1, x2, and x3, and three estimates beta 1, beta 2, and beta 3. Well, it can happen that just with the data that we've got, some estimates are actually way too large, larger than they would be in other data. In that case, rich regularization will help because it will shrink the estimates to ensure that our model works better with new data. The other type of regularization is called lasso regularization. What does it do? Well, let's say we've got a regression model. It will actually set the estimates of certain predictors to 0. Which predictors? Well, the ones that don't actually contribute anything to our model and can actually harm its performance by being in the model. ElasticNet can use both. The amount it uses of each regularization method is expressed with a certain parameter called alpha, which goes from 0, full rich regularization, to 1, full lasso regularization. The amount of regularization is expressed with a certain parameter called lambda, which goes from 0, no regularization, meaning that we've got a normal regression model, to infinity. Now, which alpha do we need to use and which lambda do we need to use? How do we integrate that with our model testing and training? Well, you can do that with nested cross-validation. Now, this slide can be a little bit daunting. Don't worry, I'll walk you through it. Let's say we've got a dataset and we perform a normal train test split. Well, then we'll be in a situation of this first bar, where we've got data where we train the model and some data where we test the model. However, depending on how you split your data, the performance of the model might be different. This is especially the case in small datasets. Well, in that case, you might be better if you split your data into k number of folds. For example, 5 folds, where one fold is used to test the performance and the other folds are used to train your model. And then you repeat that a k number of steps, for example, 5 steps here, where every fold is used as testing data and the other folds are used as training data. Then you can average the performance of your model across the folds and get a more reliable estimate. Of course, in our situation, we're doing elastic net regularized regression, and we need to figure out which alpha and lambda we need to use. Well, how do we do that? Also with cross-validation, where we test a lot of different alphas and lambdas. We train our model and then see how well our model performs with a certain alpha and lambda and see which one is best. But how do we integrate these two cross-validations? Well, with nested cross-validation. We take our training folds and only do the cross-validation for the alpha and lambda on those training folds. We figure out which alpha and lambda we need to use, train our model, and see how well it performs on the data of the testing fold. That way, figuring out which alpha and lambda we need to use is separated from the testing data. We don't see the testing data, so no information leaks from the testing data into our model. For example, in this graph, we've got 5-fold cross-validation for our outer loop, where we actually test the performance of our model, and a 10-fold cross-validation for determining which alpha and lambda is best. This is also the default setting of the NLMLapp. But how do we do a person-specific model and how do we do a pooled model? Well, in a person-specific model, you just use the data of one individual to train and test your model. However, in a pooled model, you pool all the training faults of the different individuals, train your model, and then test it on the individual testing faults of the different individuals. Now, that was the introduction into the theoretical concepts behind the NLMLapp. Now, let's move on to the app. To access the browser-based app, go to my GitHub page at github.com/Nicolas Leenaerts. Afterwards, click on the NLMLapp live repository. Then, in the Getting Started section, click on this link. Importantly, the browser-based app is hosted with ShinyLive, which is serverless. This means that all calculations are done locally on your computer. In other words, no data ever leaves your computer, which is important because of privacy. On the first page of the app, you need to upload your data. Importantly, you need to upload all the files that you want to analyze, and the files need to be Excel files. Also, they need to be complete, meaning that they can't have any missing data. As of today, I created some wrappers that integrate elastic net regularized regression with multiple imputation, and you can find these wrappers on my NLML GitHub repository. Once they're validated, I will integrate them in the NLML app. But to upload your data, click Browse, select the datasets that you want to analyze, and upload them. Afterwards, click to access the preprocessing page. Now, the preprocessing page can be a little bit daunting. There are a lot of things going on, but we'll walk through it step by step so that things become clear. The first thing you need to do is pick your model type, whether you want to make a pooled model where all your datasets are pooled, or whether you want to make a person-specific model for each and every one of your datasets. Let's start with options for the pooled model. The first thing you need to do is select your predictors. There are within-person predictors where your predictor varies within every person, and there are between-person predictors where your predictor only varies between the persons and not within the person. In this case, we'll have two within-person continuous predictors and one within-person categorical predictor. In the example, we will have no between-person predictors. Afterwards, you need to select your outcome. In this case, Y. Then, you need to select whether you want to perform a cross-validation or a train test split. In case of a cross-validation, the default number of outer faults is 5. We can simply change this. Or in a train test split, the default percentage of training data is 80%, but you can also easily change this. Afterwards, you need to define the number of inner faults that are used to determine the best alpha and lambda. The default here is 10. There is also an option to repeat the inner cross-validation to have a more stable solution for alpha and lambda. However, this is often not necessary, meaning that you can just leave it at 1. Then you need to select whether you want to stratify your faults, meaning that the distribution of the outcome is similar across the fault, or that the distribution of our outcome is similar across the training and testing data. Then you need to select whether you want your predictor scaled. This is, of course, only for the continuous predictors. In that case, the values of the continuous predictors are subtracted by the mean and then divided by the standard deviation. This will typically increase the performance of the model. You've also got the option to shuffle your data before all the other pre-processing, and this will cause that there will be no temporal contingency in the data. Then you need to select the number of alphas and the number of lambdas that are used to determine the best combination of alpha and lambda. Typically, you use 10 alphas and 10 lambdas. However, the default of the underlying data is actually 100, but this increases the computational cost by a lot and typically does not improve performance by that much. Then you need to select the seed that is used to randomize the things in the wrappers, for example, splitting the data. Typically, you just leave it at this value. You can change it if you want to, but this isn't necessary, unless, of course, you've got really small data sets where with certain randomizations, the models will not be able to run. Afterwards, you need to say which family type your outcome is. For example, if it's a binary outcome or a continuous outcome. When you've got a binary outcome, you then also need to pick the focus of the models. What is this? Well, the performance of the models with a binary outcome is typically expressed with the area under the curve. And it can be that there is one area under the curve value with multiple cutoffs, with some having a higher sensitivity and others having a higher specificity. And here you need to select whether you want to have a model with a higher sensitivity or a higher specificity. But this will only be of importance in small datasets. Then you need to select the minimum number of positive observations, so ones, in the training data. The default is 5, and this is important for the cross-validation. Why? Because every fold needs to have at least one positive observation. And then you need to select the minimum number of positive observations in the testing data, with the number being at least 1, because you need to have a positive observation to evaluate your performance. Now, these were the options for the pooled model. Let's go to the person-specific model. And almost everything is the same, except that you don't have any within-person and between-person predictors. You simply have got continuous predictors and categorical predictors, but everything else is the same. Okay, let's go ahead and make a pooled model and see how well it does. Once you've selected everything that you want in the options, you can go ahead and go to the model training and testing page. In contrast to the pre-processing page, the model training and testing page is very simple. Once you've selected everything you want, in the pre-processing page that is, you simply select Start, and the analyses start. If you've got larger datasets, then it can take a lot of time before the analyses are done in the browser-based app. In that case, be sure to download the R package and run the analysis locally in RStudio. Once your analyses are done, you can go ahead and move on to the results page, where you can first download all the results, the averages and the fold results. Then you can see some tables here, the average and median of the metrics, the full metrics, and the estimates. If a table doesn't load in the browser-based app, don't worry, they will be included in the downloaded results. Afterwards, you can go ahead to the plots page. The plots page allows you to make a plot showing a certain percentage of best predictors and an estimate on how predictive they are. There are several options you can use to fine-tune your plot, and the first thing you need to do is decide whether you want a parametric one or a non-parametric one. In a parametric plot, we use the raw estimates of our elastic net regularized regression. So for example, 0.2, 0.3, or minus 0.1. And then we take the average across the folds. In a non-parametric one, we do something differently. We first rank the predictors, meaning that the largest positive estimate is given a 1, the second largest a 2, the third largest a 3, and the same is done for the negative estimates. And then we average them across the folds. The second thing you need to do is decide the number of predictors you want to show. You do this with the percentile option. A percentile of 0.9 indicates that you show the 10% strongest predictors. If you set it to 0, that means you display all of them. The second thing you need to decide is whether you want to show a range of estimates across the datasets. But this is not important for a pooled model and is something we will discuss with the person-specific models. The second thing you need to do is choose a certain range for your plot, and you can set it to any value that you want. Then you can decide the color range, which is important for how red and how green your dots are to make your plot more interpretable. You can also choose a certain title and also subtitle and relabel the Y and X axis. Then, when you're ready and happy with your plot, just click the download button. Okay, that was everything for the pooled model. Now let's look at the person-specific models. So you can just go back to your Preprocessing tab, and instead of the pooled model, you just pick person-specific model, and again, select your predictors, continuous and categorical, your outcome, and everything else, whether you want a cross-validation or a trained test split, where you want to have a stratified folds, how many alphas, how many lambdas. But here, we'll just keep everything the same as for our pooled model, and then go ahead to model training and testing, and press start again, and wait until our models finish. And again, with the browser-based app, the analysis can take quite some time. So if you've got large data sets, be sure to look at the R package and work in RStudio or another IDE that you like working with. Once your analyses are done, go to the results page, where you can see an average and median of the metrics and estimates across the different datasets, meaning across different participants. And then you can also see the full metrics and estimates, so for every participant and every fold. Then you can go ahead and download the results. You can also go to the plots page and make a plot. For example, let's say that we want to display all predictors. And here you can also see that there's a range of the estimates across the different participants, across the different data sets. You can also choose not to display the range. When you're happy, go ahead and download the plot. Okay, that was everything for the browser-based app. Now let's look at the R package. To download the NLMLapp as an R package, again, go to my GitHub page and click on the NLMLapp repository. Then you can see 3 lines of code here that you need to download the app in your favorite IDE, for example, RStudio. Go ahead and copy them one by one in your favorite IDE and install the R package. You'll be asked to download packages that are needed for the NLMLapp, or perhaps update them. In this case, we'll just skip it all and install all of the functions that we need. Afterwards, we can go ahead and call our package and then call our app with the NLMLapp function. And then the app will open, and you can simply run all the analyses that I illustrated with a browser-based app, but just a hell of a lot faster. That was everything you need to use the NLMLapp as a browser-based app or as an R package. Of course, this is still in development, so if you see any issues, be sure to report them on GitHub or via email. If you've got any questions, you can also always ask them via email. I'm very happy to help, and have fun analyzing your data.